Okay, so the final means test that we're going to look at is the dependent T. And in the dependent T, we would ask a question such as, to what extent are student scores on your variable consistent with the final exam score? That's a pre-post test. What I'm going to use here is, to what extent are student scores on the first exam consistent with the 15th test score, which I can call the final exam. Now, what you've got to remember about the dependent T is it's very similar to the one sample T, not similar to the independent T, because really what you're testing is the difference between, in our case, test 1 and test 15. And so SPSS doesn't have a way to check for the normality of the difference without you calculating that difference. Now, what I mean by calculate is you would use this statement right here. Compute difference, and that's a new variable. That's a variable that you have created yourself just by naming it. If you write this out, compute difference, it understands that you're naming this new variable, and then you say equals, and you have to use the two variables that you want to compute a difference of. And you can name it something else, whatever you want to name it. I named it difference, and because I'm looking at test 15 and test 1, I put those names in, put a minus sign in between them, and I put a period there. Don't forget the period. Now, be very careful when you're writing out your variable name. The variable name must be exact, otherwise SPSS will not recognize it. So for example, if you put test space 15, it won't recognize it because the space it doesn't accept, so you get an error. So make sure you don't have a space in there if your variable doesn't have one, which it shouldn't. And then you put execute, and SPSS will create a new variable called difference. Once you've created that new variable, then you can run your examine to get the QQ plot and everything we're used to seeing when we're trying to examine the variable for normality. And then here's the syntax for the t-test pairs, and I've said test 1 with test 15, and then the criteria. Now, actually, I should put test 15 with test 1. That way it comes out in the same direction as this one. And what I mean by that is I want test 15, the later test, minus the first test. That way if I get a positive score, that means I did better on test 15. If I get a negative score, that means I did better on test 1. So, you can easily change that in your syntax. So here's how you click through there. You go to Analyze, Compare Means, Paired Sample t-test. And so the paired sample t-test, when you click on that, you'll get your pop-up box. And in your pop-up box, it looks very different. Here you're going to put variable 1 and variable 2. Because again, a paired test involves two variables, intervally scaled. And so in my case I put test 1 and test 15, but again I would reverse this order so that that comes out reversed. And then you hit paste and you can run that. And what you get, because remember we asked for the difference, you can also put test 15 and test 1 here so that you can get the plots for all of them. I just forgot to do it there, but I'll do it when I run it. And what you get is descriptives for difference, which is the variable, in my case, test 15 minus test 1. And the mean difference between those two is 12 points. And that means that the student scored about 12 points higher on the final exam than they did on the very first exam. And that difference, the 95% confidence interval, is between 11.25 and 12.98. Here you can see the skewness and kurtosis divided by the standard error, and this tells us since the values are less than 3, if you're really being conservative you could say less than 2, but the values are well within the range of what you would expect for a normal distribution. The KS test is not statistically significant. Remember, we're looking for a value less than 0.05. The Shapiro-Wilks is not statistically significant. Again, we're looking for a value less than 0.05. So everything we see here in the test says that this is a normal distribution. What is a normal distribution? The difference, which is that new variable we created, that is the difference between test 1 and test 15, because that's what we have to test, and our assumption of normality is on the difference. It's not on the individual test, it's on the difference, because in a paired t-test what we're testing is the difference between two means. Here's our normal QQ plot, and you can see that this is very nicely, you know, there's a little curvature there at the ends, like, but very well tied to the line, and so I would conclude that this is normally distributed, that the difference between the two means is normally distributed. So that's good. That's one of your assumptions for the t-test. And for the dependent t, because you're working with the difference between the two scores, you're not looking at two individual scores, you can't really think of homogeneity of variance because you only have one set of scores that you're examining. And that set of scores is the difference between test 15 and test 1. Okay, so let's pretend that these are the scores that you have. You have test 15, and the first score is 93, the second one's 88, and so on till your last score where you have a 90. Test 1, 87, 70, all the way to 85, right? And so you have all your scores here in test 15, your last test, all your scores here in test 1, and you take the difference between them. Here we have 6, here we have 18, here we have 5. And so what we're dealing in the in the dependent t is you are dealing only with this column. You're not dealing with these individually. So you can't look at homogeneity of variance because there's only one set of data that you're looking at, the difference score. And it's this difference score that needs to be normally distributed. It's and just like in the one sample t, it makes no sense to talk about homogeneity of variance because you only have one set of scores. In this dependent t, it makes no sense to talk about homogeneity of variance because you only have the difference score. And so I just wanted to make sure that that was clear, because you do start with two sets of scores, but your focus is on the difference between them. So let me move this. So of course, if you use the examine syntax, you can find the descriptives for test 15 and test 1, or when you run your t-test also you'll get the descriptives, but a lot smaller table. Here you get 95% confidence intervals and so on. So this is given to you with the paired sample statistics, but you also get two other things. You get the paired samples correlation, which gives you an indication of the relationship between test 15 and test 1, and you also get the paired differences confidence interval. So you don't get the confidence interval in the paired sample output that you get if you had done them individually, but you do get the confidence interval for what you're actually looking at, which is the difference between the two means. And the confidence interval for the difference between the two means is this 12.98 and 11.25. That's the confidence interval for the paired sample t. The mean difference between them is 12.11. The standard deviation is 7.6. Again, of that distribution that we're interested in, which is called difference, which we had SPSS actually calculate for us. And of course it calculates it when it does the t-test paired, but the reason why we had to compute it on our own was because we needed to get the test for normality for that difference. And if we had not computed it or asked SPSS to compute it, we wouldn't know whether it was normally distributed or not. Okay, so now let's look at the information. We can see the value for the t, we can see the degrees of freedom, and the statistical significance says it's 0.00. Never, ever, ever report a p-value of 0, because what that means is the probability of you getting that statistic is impossible, is 0. So how in the world did you get that statistic if it's impossible? You didn't. What that actually means, and if you double click on SPSS, you'll be able to get more places after the decimal. What this means is it's a value that has numbers beyond those 3 that are seen. So what you report when you see a p-value like this is you report p less than 0.001. So what can we say in general? Well, we can say that the student scored statistically significantly higher on the 15th test than on the first test, because we see a mean difference of 12, and we see that the t is statistically significant. Furthermore, if we use the effect size Excel sheet that I gave you and you calculate the Cohen's d, you can provide the Cohen's d of 1. So then we look at our t statement, where we have t 2.99, or 299, I'm sorry, that's the degrees of freedom. 27.61 is the t-value, p less than 0.001, and don't forget a space before and after. In this case it's not a equal sign, but it's a less than sign, and then the Cohen's d of 1.59.